Internet channel. Please do remember, subscribe, like and share. Thank you. Hi all. Today we are going to discuss about solubility equilibria. This is the last topic in chapter 7, chemical equilibrium. Are you ready? Let's start. First, what is solubility equilibrium? Previously, we learned about chemical equilibrium, ionic equilibrium. So what is solubility equilibrium? Solubility equilibrium is the equilibrium axis between solid, solute, and aqueous ion. So this is in solid, this one is in aqueous ion. For example, lead chloride is a solid, and then dissociate from the lead ion and chloride ion. So if the solubility equilibrium means the solid solute and the aqueous ion at equilibrium. Another example is silver sulfide. When it dissociates, you form 2 mole of silver ion and 1 mole of sulfate ion. Example of the solid which can dissolve in water or insoluble in water. First, lithium chloride, soluble, but lead chloride is insoluble. Next, potassium hydroxide, soluble, but copper hydroxide is insoluble. Sodium carbonate, soluble, salt, but calcium carbonate, insoluble. Sodium nitrate and lead nitrate both are soluble. So the solubility actually is related with our Form 4 concept, salt. There are few salts 100% ionized, for example, nitric salt. Okay, next. This is the solubility rules for common ion compound. Compound containing alkali metal ion and ammonia, soluble. Nitrate, bicarbonate, chlorate is soluble. And then all chloride, bromide, iodide salts are soluble except silver, mercury, and lead. And then all sulfate is soluble but except silver, calcium, strontium, barium, mercury, and lead. Okay, these all are insoluble compound, but except just now we mentioned over here, right, ammonia. So all ammonium salt is soluble, and for hydroxide is insoluble except compound containing alkali metal ion and barium 2+. So for example, just now potassium hydroxide is soluble. So the appearance of several precipitate. Okay, so this is CDS, PBS, in different color. Okay, the color is nice and beautiful. Okay, next. If we discuss about solubility of solute, we will look at molar solubility and solubility. Both of them with different unit. Let's solubility, the unit is in gram per liter. The mass of solute that dissolve in a given quantity of solvent to form saturated solution. So remember, solubility is gram per liter. Okay, we are using the mass of solute over the volume of the solution. Okay, next. Molar solubility, the unit is in mole per liter. Okay, mole of solute dissolved in 1 liter of saturated solution. But there is one point. When the question given didn't mention is solubility or molar solubility, normally it's referred to molar solubility. Please take note. Okay, next. Solubility product, KSP, is the product of the molar concentration of the ion involved in the equilibrium, each raised to the power of its stoichiometric coefficient in the equilibrium equation. KSP, actually the concept still like Kc, Kp, Ka, Kb. Ignore solid and liquid. So it's provide a quantitative measure of solubility of a slightly soluble salt, only for slightly soluble salt. That's why the error is still reversible. So for example, calcium phosphate, it will form the calcium 3 mole of calcium 2 plus ion and 2 mole of phosphate 3 negative ion. So the KSP is concentration of calcium 2 plus to the power of 3 because based on the coefficient. Okay, and then a PO4 phosphate 3 negative, okay, to the power of 2 because based on this coefficient. Solid, ignore. So in this case, we must know how to write a proper equation for the dissociation of the solid compound into ion, and then make sure you have write down the balance equation in order to write down the correct KSP. Solubility product constant KSP of selected ionic compound at 25 degrees Celsius. There are few examples, okay, meaning that all of these are slightly soluble salt. Keep in mind, soluble ionic compound 100% soluble and dissociate in water such as sodium chloride has no KSP value. Okay, so for example, the strong acid, strong base, there's no Ka and Kb value. Let's try example 1. Write the solubility product KSP expressed for each of the following. As we know, right, all of this right is salt. Okay, so it's in solid form. That's why it will start with the solid. Silver carbonate, you have to know the molecular formula, the formula for silver Ag, carbonate CO3. So silver with positive charge and then CO3 with 2 negative. So make sure that the molecular formula, okay, for silver carbonate is correct. Same for the others. Let's check one by one. Silver carbonate. Okay, so Ag2, because silver is with positive 1 cation, and then CO3 2 negative. That's why there are 2 silver. That's why 2 mole silver ion is produced, and then 1 mole carbonic ion is produced. So this is the KSP. Silver to the power of 2, okay, and then this one to the power of 1. Barium fluoride, barium with 2 plus, fluoride with negative 1, that's why F2. So 1 mole of barium 2 plus react with 2 mole of fluoride ion. Must remember phase insist. So for all the salt is in solid form, and then the ion is in aqueous form. Okay, and the write out the KSP product. Okay, suppose it's product over reactant, but the reactant is solid, so just ignore. So this is the KSP. Copper sulfate Cu2 plus S2 negative, that's why 1 to 1. Okay, this is the KSP for copper sulfate. Iron hydroxide, iron 3 plus hydroxide negative 1. That's why 1 mole iron is formed and then 3 mole hydroxide is formed. So the KSP is iron 3 plus to the power of 1 and then hydroxide to the power of 3. Barium with the charge of 2 positive and then phosphate with 3 negative. That's why you form 3 mole of barium sulfate, 2 mole of barium and 2 mole of phosphate. So the KSP is barium 2 plus to the power of 3 and then phosphate 3 negative to the power of 2. Tin is Sn. Take note, if tin is referred to Sn with the charge 2 plus, sulfate with the charge 2 negative, that's why it's 1 mole to 1 mole. So this is the KSP for tin sulfate. So after you try these six salts, right? You must know the charge of the cation and anion in order to produce the correct number of mole or the coefficient of the ion. Okay, next is about calculation involving KSP. After the definition, and then you understand what is solubility, molar solubility, and solubility constant. Now we proceed with calculation of KSP. There are 2 types of calculation. The first one is determine the KSP from the solubility or molar solubility, or reverse, determine the solubility or molar solubility from KSP. So let's try some example. Again, for this part, we need to use ICE table. Similar with the calculation of Ka and Kp. So step 1, write down the balance equation, phase insist. Step 2, I form the ICE table. Step 3, write down the KSP expression. Step 4, answer the question accordingly. and then you have to make the conclusion for step 5. So look at 1. Calculate the molar solubility of lead chloride, and then KSP is given. So we check the step. Yes, step 1. Write down the equation. Phase insist. Always remember it's reversible error. Then for the reactant, there is nothing because it's in solid, so ignore. The concentration of the product is equal to 0, 0. And then the change is according to the coefficient. Here 1 mole, that's why positive S. And then here 2 mole, that's why positive 2S. And then sum up, so S and 2S at equilibrium concentration. Okay, after unstable step 3, write down the KSP according to this equation. Concentration of lead 2 plus ion times concentration of chloride and ion with 2 to the power of 2 because 2 mole. So S times 2S squared. So you have to remember to the power of 2 also. 4S squared times S, so equal to 4S cubed. 4S cubed equal to 1.3 times 10 to the power of negative 5. Now you have to find out what is the solubility. What is the molar solubility S? So you insert, okay, 3. So you get 1.6 times 10 to the power of negative 2 molar. Remember, unit insist. And then the last one, make the conclusion. So the molar solubility of lead chloride is this value with unit molar. Okay. KSP of copper hydroxide is given, and then calculate the solubility of copper hydroxide. Now it's in gram per liter. Just now didn't mention anything, means it's in molar solubility. For this case, mention gram per liter, so it's solubility. But before that, we need to find out the molar solubility first. So again, with the same one, write down a balanced equation with the phase solid aqueous. Okay, the concept for the unstable still the same. And then number 3, step 3, write out the KSP expression, substitute, and then we successfully find out the is 4S cubed. So you insert, okay, and then you equal to this concentration. So this is the molar solubility of copper hydroxide. Okay, that's why step 5 haven't finished yet. You have to continue because the question 1, the solubility in gram per liter. So step 5, we successfy the molar solubility, and then we haven't complete yet. We have to continue because the question asks about solubility in gram per liter. So you have to know from molar solubility to solubility, we need to times molar mass. And then from solubility to change to molar solubility, we need to divide it by molar mass. So in this case, we need to find out the molar mass of copper hydroxide. So then convert the 1.8 times 10 to the power of negative 7 molar to gram per liter by times molar mass. So we will get 1.8 times 10 to the power of negative 5 gram per liter. Over here, mole copper hydroxide cancel, and then the unit is gram per liter. So 1.8 times 10 to the power of negative 5 gram per liter is the solubility of copper hydroxide. Here. Next, using KSP to compare solubilities. Okay, like previous, K increase, acidity increase. So in this case, KSP increase, solubility increase. So based on these two equations, magnesium carbonate and lead sulfate, okay, this is the balanced equation. And then we check the KSP for both of the solution. Okay, this one, okay, is smaller. This one is higher. That's why magnesium carbonate is more soluble than lead sulfate. So always remember, must compare KSP of compound whose formula have same total number of ion. So over here is 1, 1, so equal to 2, 1, 1 equal to 2. Now we have to compare KSP with QSP. Like last time, the reaction quotient, the Q value, QC and KC. Concept still the same, but this one is predict the formation of precipitate. So there are 3 situations. So the first one is when the QSP equal to KSP. Okay. QSP over here we say is ion product. Formula same as KSP, product over reactant. Okay. the system is already at equilibrium when QSP equal to KSP, so the solution is saturated with a soluble ion and no change occur. So this is the saturated solution. The aqueous ion and the solid ion is at equilibrium. So equilibrium exists between the undissolved solid salt and its dissolved ion. Okay, for example like this. Next, if QSP larger than KSP, Q higher meaning that form more product. So this solution is supersaturated precipitate form. So the system shift to the left to reach equilibrium until the solution is saturated, means QSP equal to KSP. Here, if you still remember, right, okay, Q higher meaning that form more product. That's why the product need to shift to the reactant side. That's why the system shift to the left side. Okay. When QSP is smaller than KSP, meaning that the solution is unsaturated, no precipitate will form. So the system shift to the right to reach equilibrium. More salt should be dissolved. You have to add more salt to increase the ion concentration until QSP equal to KSP. After we learn about comparison between QSP and KSP, let's check for one exercise. Example 4. Will a precipitate of calcium sulfate form in a solution if the calcium ion concentration is 0.025 molar and the sulfate concentration is 0.030 molar? Meaning that in this case, we need to write out the equation and then find out the product of these two ions, and then we compare with the KSP value, whether it's the same or not, or smaller or higher. Yes, first write out the balance equation. It's a reversible reaction, solid calcium sulfate, and then form calcium 2 plus ion in aqueous, and then sulfate 2 negative in aqueous. And then the KSP, okay, concentration of calcium 2 plus ion times concentration of sulfate ion is 2.4 times 10 to the power of negative 5. This is KSP. And then based on the given concentration, okay, we try to substitute over here for the QSP. QSP actually is the same with the KSP. But so after substitute, we get 7.5 times 10 to the power of negative 5, meaning that QSP is larger compared to KSP. So in this case, the solution is supersaturated. So the system will shift to the left to reach equilibrium until the KSP same as QSP. Common ion effect. This is the last subtopic for this chapter. Before we continue with this topic, let's listen to a story. A university offers 20 seats for medicine course. 20 classmates of your class want to apply it. At the same time, 20 students from another class also want to apply this course as well. Now, the common ion effect is like the number of students. The chances to get the course decrease. So, what I explained just now is the analogy of common ion effect. Student is the common ion. All of them go to apply this medical course, so the chances to get this course decrease. So the story is the same as this theory. So common ion is an ion that is common to two or more compounds in a mixture of a solution of iron. So this can reduce the solubility of salts in the presence of a common ion. So less solid can dissolve. Let's check what is the effect of common ion on solubility. The presence of a common ion will decrease solubility of slightly soluble ionic compound. For example, the addition of sodium chromate soluble salt to a saturated solution of lead chromate. So we can represent the lead chromate with this equation. Dissociate will form the lead ion and chromate ion. And then we have to apply the Le-Chatelier principle. When the sodium chromate ion is added, what happens? the concentration of the chromic ion increase. So the system will shift to the left. Now, this is the KSP. Okay. When the system shifts to the left, it can reduce the concentration of lead ion and chromic ion. Then, effect of the addition of common ion in chromic. So the concentration of this one increase, then some chromic will join or combine with lead to form more solid Pb chromic. Okay, lead chromic. Meaning that the solubility for this one decrease. Common ion effect, let's check with one example. Example 5, what is the molar solubility of silver bromide in pure water and 0.001 molar sodium bromate? KSP is given. So first, let X equal to molar solubility of silver bromide in pure water. So first, write out the equation. Okay, always remember it's a reversible equation, and then solid, so silver bromide, partially slightly soluble salt, and then silver plus aqueous plus bromide ion aqueous. So the initial concentration, change of the concentration, and equilibrium concentration. I think you're all quite familiar with this one already. From Kc, Kp, now Ka, Kb, now is Ksp. Okay, 0, 0 at the reactant product side. Okay, so positive X, positive values on the coefficient. So this is the concentration of the species at equilibrium. So Ksp is concentration of silver plus times concentration of bromide ion. So X times X equal to X squared equal to this value. And then we set this value and then we get the X equal to 0. The molar solubility is of silver bromide in pure water is 8.8 times 10 to the power of -7 molar. Next, less S. Just now using X, now we using S. Is the molar solubility of silver bromide in sodium bromate. So concept still the same, balance equation, I stable. But for this case, the initial concentration of bromide ion is 0.001. Then the change, positive S, so sum up, okay, this is positive S, this is 0.001 plus S. Okay, we assume that S is very small, that's why we ignore the S, so it's meaning that this is equal to 0.001. Okay, so KSP straight away you substitute S times 0.01, you get 0.001 S. So what is the S value? Okay, just normal calculation divided by 0.001, so we get 7.7 times 10 to the power of -10 molar. This is the molar solubility of silver bromide in sodium bromate. Okay, with this case, this solubility, molar solubility. Okay, if we extend the question, ask you to compare. So what happened? So based on the value here, right, you will notice, okay, the molar solubility of silver bromide in sodium bromate is lower. Why? Because the presence of the common ion Br in sodium bromide solution increase the concentration of the bromide ion, and more bromide ion will react with the sodium. With the silver. Okay, more bromide ion will react with the silver. Thus, the shift of the equilibrium will shift to the left. Hence, increase the formation of silver bromide and decrease or reduce the solubility. Here. Tutorial question. See you in next video. That's all for this video. Please do remember, subscribe, like, and share. If you have any question, please don't hesitate to consult with your lecturers. Stay at home, stay safe. Bye.